everyone, and welcome to today's webinar in the CERDP and ESTCP webinar series. My name is Rula Deeb. I'm a Senior Principal at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of CERDP and ESTCP. I will be facilitating today's call. The webinar will consist of a brief overview of CERDP and ESTCP, followed by the technical portion of the webinar. The event today focuses on DoD research efforts on the use of advanced nanocrystalline alloys as alternatives for repair and replacement of high-wear parts. First, Dr. Jonathan McRae from Integrin Technologies will talk about the development and performance of nanocrystalline cobalt alloys and composites as alternatives for chromium and nickel plating in repair operations. His presentation will be followed by a brief question and answer session. Second, Dr. Alan Reeves from the U.S. Naval Air Systems Command will discuss the qualification testing of electroformed nanostructured cobalt alloy bushings as cost-effective replacements for copper beryllium alloys in manufacturing high-strength aircraft bushing. Dr. Greaves' presentation will also be followed by a Q&A session. We will then conclude the webinar with an interactive Q&A session with both of today's speakers. Today's broadcast will be listen only. You may submit questions by using the chat box in the lower left-hand portion of the screen. You do not need to wait until the Q&A periods to submit your questions. In fact, we encourage you to submit questions well in advance of the Q&A sessions. On this slide, we have provided a few suggestions in case you experience technical difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen or call into the conference line shown here. However, if you continue to have problems, please submit a comment using the chat box in the lower left corner of the screen. With that, I would like to introduce Dr. Robin Nissan, who is the CERDP and ESTCP Program Manager for Weapons Systems and Platforms. Before joining CERDP and ESTCP, Robin worked at Navarre's Weapons Division, China Lake in California. Robin? Robin, please proceed.
Thank you very much, Rula. I'm very pleased to welcome everyone to today's CERDP and ESTCP webinar. And CERDP is the Strategic Environmental Research and Development Program. It was established in 1991 by Congress as a partnership between the DoD, Department of Energy, and the EPA. CERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. CERDP funds both fundamental research as well as advanced technology development, which we hope will ultimately impact real-world environmental management. ESTCP is the Environmental Security Technology Certification Program. In this program, we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under CERDP or other research programs and are designed to transition technologies out of the laboratory and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation as well as to regulatory acceptance. CERDP and ESTCP are complementary programs with much of CERDP research occurring in the laboratory and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted as well. Okay, so there are 4 program areas in CERDP and 5 in ESTCP. Installation, Energy, and Water program is only an ESTCP program area, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Resiliency, as well as Weapon Systems and Platforms, have components in both CERDP and ESTCP and are jointly managed by one program manager. Okay, slide 12. Our webinar today is focusing on research and demonstrations that were and actually are being conducted under the Weapon Systems and Platforms program area. This program area has essentially 5. So we're on slide 12, right? Yeah. Okay. Okay, so Weapon Systems and Platforms has 5 program areas. Surface engineering, which these projects fall under, as well as energetic materials and noise and emissions and lead-free electronics is another area that we have some efforts in. Okay, going to slide 13. Okay, yes. The webinar series highlights R&D efforts from each of our 5 program areas, which I mentioned earlier. And as you can see, we have upcoming webinars covering a broad range of topics, including sediment, volume, search, sonar, enhancing ecosystem-based management under coastal installation, tools to evaluate passive, active remedial approaches at chlorinated solvent sites, approaches to managing threatened and endangered and at-risk bird species, as well as energy, sustainable wastewater treatment systems for forward operating DoD installations. The next WP webinar is scheduled for May 31st and will focus on resonant acoustic mixing of energetic materials. Slide 14. You can find more information about upcoming webinars using the link shown here. Registration is live for webinars through the end of the calendar year. I would like to remind you that a copy of today's presentation can be downloaded from our webinar webpage, and we would appreciate it if you could please take a moment to complete the survey that will pop up on your screen at the end of the webcast. And finally, I'd like to mention that we are planning, I'm very, very excited about this, we're planning another CERTIP ESTCP Symposium. It will again be held in the Washington, D.C. area at the end of November, the week after Thanksgiving. It's a 3-day event and will showcase the latest technologies that enhance DoD's mission through improved environmental and energy performance. Registration information will be available shortly on the CERTIP and ESTCP website. Thank you, everyone, and I hope you enjoyed today's webinar.
Thank you so much, Robin. And we're about to get started here with Dr. Jonathan McCree, who is the Vice President of Technology for Integrin Technologies. He has worked with Nanostructured Materials for over 20 years. Dr. McCree has served as the PI for multiple DoD-funded programs, which provided fundamental research basis for developing environmentally benign nanocrystalline cobalt alloy coatings for hard chrome alternatives. Dr. McCree is the author of over 30 scientific publications. He received a bachelor's degree in metallurgical and materials engineering from Queen's University in Canada, and a doctoral degree from the Department of Material Science and Engineering at the University of Toronto. John?
Yes, great. Thank you, Rula. So first off, I'd like to thank everyone for logging in today and taking the time to listen to some of the exciting work we've been doing on our CERDRIP project and as well the ESTCP project working with Alan. So our project that I'll be talking about today is this current CERDRIP project where we're looking at our nanocrystalline cobalt alloys and developing composite materials and looking at them as alternatives for chromium and nickel plating, specifically looking at repair operations. So a quick breakdown of the talk today. I'll go through the problem statement, the motivation behind the work, what we've been working on as the proposed solution. Then I'll go into some details regarding the current project, what the objectives are, some of the results to date, and how they benefit the DoD, and very quickly highlight the next steps in the project. So the main problem that we've been addressing in this project over the years has to do with the environmental and health risks associated with hexavalent chromium plating as well as nickel plating. Both hexavalent chrome is a known carcinogen, and the OSHA PL has recently been reduced from 52 to 5 micrograms per meter cubed. So that, combined with the inefficiency of the plating process and the mists involved with depositing chromium coatings, makes it more difficult to comply with all the regulations. So a need for an advanced alternative that can compete both on a process and cost perspective is needed for these technologies. So Integrand's main technologies involve nanostructured materials. And we started the original project with the question of, can a nanometal coating provide a suitable replacement for hard chrome? So first off, I'll just very quickly describe what we mean by a nanostructured metal. So a nanostructured metal is simply a metal coating that has a grain size in the range of 10 to 100 nanometers. So conventional metals are crystalline and they have grains. And the grain size of a conventional metal is between maybe 10 and 100 microns. So with a nanostructured material, you just simply reduce that grain size. So the grain size is in the order of about 20 nanometers. And by doing so, you get very interesting property changes, specifically as it relates to the hardness and the strength of the material. As an example, going from a conventional nickel with a 20 micron grain size to a nanocrystalline nickel with a 20 nanometer grain size, you get an increase in yield strength from about 100 megapascals to about 900 megapascals. And similarly, you get an increase in hardness from 140 to about 450 Vickers hardness. So you see tremendous property changes when you just simply reduce the grain size of the material. So the way that we create our nanostructured materials are through a pulse electrodeposition process. So similar to chrome and nickel, it's made in an electrodeposition process. So you produce the coatings in aqueous baths, you apply a current, and you deposit the metal ions in the solution onto your substrate in the form of a coating. So traditionally, we've used pulse electrodeposition in order to create the fine-grained structures. And what you'll see, what that achieves is a very fine-grained uniform structure throughout the thickness of the coating. In conventional plating, typically you see a fine-grained structure right at the interface. However, as you grow to thicker structures, you commonly find the grains elongate to larger grain sizes. Through the use of pulse plating, you can favor the nucleation of new grains over the growth of existing grains, and this results in an ultrafine grain structure through the thickness of the coating. And the ultimate end result of the coating is a fully dense metal with a nanocrystalline grain size. And I should mention at this point that there's no powders involved with the production process. We go from ions in solution to fully dense metal on the plate, and there's no intermediate powders that are involved. So one of the objectives of our current project, in fact, was looking at whether or not we can produce these structures without the use of pulse plating. So I'll go into that a little bit later when I talk about the project. So after many iterations and looking at a number of different materials, we settled on a cobalt phosphorus alloy composition as the preferred solution as an alternative for hard chrome. So the nanocobalt phosphorus is simply an electrodeposited nanocrystalline cobalt phosphorus alloy. So it's primarily cobalt with about 1 to 2% phosphorus, and it's electrodeposited with a grain size between 10 and 20 nanometers. It's a cost-effective process, and similarly to chrome, it's done through electrodeposition, and it provides significantly improved corrosion resistance, lower friction, better ductility and toughness compared to electrolytic hard chrome. And there's now a military specification as well as an AMS specification for the process. A quick comparison between the processes for nanocrystalline cobalt phos and electrolytic hard chrome. One of the big advantages of the cobalt phos is the faster plating rate than chrome. So it plates about 5 times faster. So this can result in increased throughput, and you can replace several hard chrome tanks with one cobalt phosphorus tank. And the bath is very stable. So going through the parameters, the nano cobalt phos plates, traditionally it was with pulse plating. We're looking into DC plating compared to DC plating with electrolytic hard chrome. It can plate line of sight and non-line of sight surfaces. It has a very high efficiency, so this is the conversion of the electrical current that you put into the process versus how much of that goes to producing or reducing the metal versus producing hydrogen. So it's much higher than chrome, resulting in a faster deposition rate compared to chrome. The other advantage is since you're not producing a lot of hydrogen at the cathode, you have significantly less gassing that comes off the process and a lot lower mists. Through the emission analysis that we've looked at, there's been well below the OSHA limits for cobalt. And the bath temperature is a little bit higher than that of chrome, which we're addressing also in this current project in a little bit, which I'll talk about a little later. So there's a lot of work went into the cobalt phosphorus development to date. So I won't go through all the property comparisons, but one in particular that I'll just mention today is regarding the corrosion. This is a salt spray corrosion compared to hard chrome. And this is an area where we see significant improvement. So we've tested it out against a number of electrolytic hard chrome vendors, and we see that the time to red rust with the cobalt phos is significantly higher, going from about 200 hours to time to red rust to over 1,200. So this is really one of the areas where it performs very well. And the reason for this performance increase is due to the structure of the coating. This slide here shows micrographs of the nano cobalt phos coating compared to that of hard chrome. One of the reasons why hard chrome doesn't do so well in salt spray corrosion is it's microcracked, and these microcracks eventually open up and lead to a pathway where the atmosphere and the environment can penetrate, rusting the substrate, and then that's when you see red rust. With the cobalt phos, it has very good corrosion protection as well as there's no cracks. So the substrate is protected, and you see that's one of the reasons why you see much longer times to red rust. So comment here on the plating. This slide here shows your typical what a typical plating line looks like. This is the picture up here on the right is the plating line at Fleet Readiness Center Southeast in Jacksonville, where there's a tank has been installed. And then this tank down here is the tank that we have at our facility here in Toronto. The process is it's a very stable process. The tanks have been in place, or the tank in our facility has been in place since 2005, and it's the original solution that we're still using in the process. A successful ESTCP demonstration validation was completed in 2005, and resulting in a number of good properties and good property data supporting the use of the coating for a number of applications. So then summarizing the history of the development, here's a timeline showing the original project, which developed way long in about 18 years ago. and then through its progression through the ESTCP DEMVAL projects, and then as well as the release of the mill standards and the AMS standard. So yeah, it's been what we've learned in this project is the time it takes to develop a new material and to get it qualified. But to date, it's been a very successful project, and we're very happy with it. So on that note, now I'll move on to our current SURDRIP project, which is SURDRIP WP 2609. And in this project, the objective of it is to look at it less as a replacement for hard chrome, or including nickel plating in that, and specifically targeting repair operations. So we're looking to develop and validate an alternative repair technology based on the nanocrystalline cobalt phos alloy, as well as address some of the usability issues that have been identified in the past. So specifically what we're looking at doing is trying to meet and exceed the properties of both nickel coatings and electrolytic hard coatings according to the various mill standards, and as well demonstrate that it can be used for selective plating and repair operations in order to rebuild worn parts. So the project team that we're working with on this project includes us here at Integrand Technologies, and we've also partnered with a company called Cirrus Material Science, and they're located in New Zealand, and they have a very interesting new technology that basically forms very small nanoparticles in the solution which co-deposit at the interface during the deposition process. We've also partnered with Cordessa, who's looking at the electrochemical modeling of the various new matrices that we're looking at, and again working with the Fleet Readiness Center, Ruben and Jack at Navarre as the ultimate stakeholder and end user of the technology. So the project objectives that we're looking at in this project, we divided into three main areas, and we're looking at basically looking at the material for use in repair operations, but also seeing ways that we can improve the process and performance. So the first project objective involves looking at ways that we can optimize the current cobalt phos process, where we're looking at ways and modifications to the chemistry so that we can do direct plating. We're also looking at ways that we can lower the plating temperature of the solution to make it a little more compatible with existing kind of processes at Fleet Readiness Center. And then since we're also looking at potentially repairing aluminum structures, we want to look at whether or not there's any tweaks we can do to make it more suitable for coating aluminum substrates. And the second main objective area involves looking at using the cobalt phos metal coating and then incorporating the particulates, various hard phase particulates, for enhancing the wear properties. And we're doing this with a dual approach. One, the conventional method of adding particles, suspended particles to the solution and co-depositing the particles, as well working with Cirrus to look at the novel in situ particle formation and deposition of the very, very small nanoparticles using the Cirrus dopant technology. And then the final objective is looking at this technology and seeing how it can be applied specifically in brush plating and selective repair operations. So this slide here shows the strength of the materials. I thought it was important looking at the coating as more as a repair coating. One of the important materials is whether or not the coating actually provides any structural benefit to the substrate. So this slide shows a number of stress strain curves for different materials. So through a uniaxial tension test. So in this test, you load up the sample and you increase the strength, and it measures the strength in the material until it fails. So what it shows here is there's a conventional polycrystalline cobalt material which has a UTS of about, say, 750 megapascals. Now, when you decrease the grain size of the cobalt to, say, 20 nanometers, you get an increase in strength to over 1500 MPa. And then when you further alloy with phosphorus, you get a further increase to over 2000 MPa. So this shows the benefit of reducing the grain size as well as solid solution strengthening with the phosphorus. But the other main point to look at is that the ductility hasn't changed. So we're still getting over 5% elongation before fracture. So this shows that even though you get tremendous increases in strength, you still have a tough material that can be used structurally. And when you compare it to conventional nickel and aluminum, you can see that the coatings are actually much stronger, leading to the possibility that you can facilitate a structural repair without flaking or spalling during high levels of strain, but also the possibility that you can further enhance the properties of the part that you're coating. So now I'll move into some of the results that we've had in our project. So related to the objective number 1, where we're looking at further optimization of the process, we're looking at both using direct current rectifiers as well as lowering the plating temperature. So we conducted a number of design of experiments where we looked at various process and chemistry parameter tweaks. And then through that, we were able to identify a window of operation that results in being able to plate at slightly lower temperature as well as using direct current as opposed to pulse plating. And this is mainly due to the addition of some chemistry and some additives. But the big benefit is now there's a nice, slightly enhanced operating window for lower temperature, as well as increased current density and direct current plating. After initially identifying the window of operation, we produced a bunch of panels and compared various properties against the standard operating conditions. So we found that compared to standard operating conditions, everything matched up very well. The hardness was in the similar range. The abrasive wear resistance was kind of very similar, and we still had good sliding wear and coefficient of friction as measured in pin-on-disc testing. So the second part of Objective 1 was to see if we can kind of tweak the process in order to more readily coat on aluminum. In the past, we have been able to use the standard process to coat on aluminum. However, the high temperature of the process as well as the lower pH of the process did result in some concerns with coating onto aluminum, since the solution was fairly aggressive if any aluminum was exposed while you're coating. So if you're fairly encapsulating and putting a part in, coating all surfaces, it's no problem. But if you're masking certain areas when you're coating aluminum, if there's any issues with the mask, then you could have some corrosion. So we looked at modifying the chemistry specifically for plating onto aluminum substrates, and were quite successful and developed a slightly new process, which we call the 3311, which was able to successfully coat onto the aluminum without any risk of damage. So what we show here on this slide is a comparison of the hardness between aluminum and the cobalt coating, showing a very high increase, so that would be better surface durability. And then we did a flexural test on an aluminum bar coated with just 50 microns of the nanostructured cobalt alloy. And what you see in this is that you see a tremendous increase in the flexural strength of the aluminum substrate just simply by putting a 50 micron coating on. So that demonstrates that potentially there is room for enhancement of properties with the nanostructured coating. So the other advantage of the Cobalt Phos when looking at coating steel and aluminum substrates compared to nickel and chrome is the corrosion potential of the Cobalt Phos. The open circuit potential is closer to that of steel and aluminum, so ultimately likely resulting in a lower driving force for galvanic corrosion between the coating and the substrate. Ultimately, hopefully leading to better long-term performance, corrosion performance. So the second objective that we looked at was enhancing the properties, or mainly the wear resistance, through the incorporation of various hard phase composite particles. So again, we did this using two methods. One was just the conventional way of putting particles into the solution and co-depositing the hard phase particles, and the other was through the use of the Cirrus dopant. So we were successful in co-depositing various particles. I believe we looked at a number of different particles and a number of different particle sizes. And what we saw, the graphs here shows both the hardness as well as the abrasive wear resistance as measured from the Tabor wear test. The Tabor wear test curve is in red and the hardness is in blue. So what we saw in all cases, the incorporation of particulate increased the hardness of the coating. And as well, we saw a decrease in the Tabor wear from about 18 down in some cases to about 4. So we were quite happy with these results showing the benefit improvement. The Cirrus dopant, we found that it did increase the hardness, and the Tabor wear results, the abrasive wear results did improve. However, when we looked at the cross-sections of the coating, we felt that there wasn't sufficiently enough particles co-deposited to result in a significant decrease in Tabor wear. And Cirrus is currently optimizing their process and has recently resulted in new dopants that we're currently testing, and we're hopeful that they result in even better performance than we're seeing right now. So in the last objective that we looked at was taking this new technology, the new process, and applying that to selective area repairs. First, we looked at brush plating. So you have basically, rather than dipping your part in your tank, now we're using brush plating to flow solution through a brush plating head onto a sample and then coating it. So we produced a number of samples and we looked at the hardness as well as the Tabor wear. And we found that we were able to increase, so we saw similar performance of the tank plated material as we did with the brush plating. So we saw a significant reduction in the Tabor wear as well as an increase in hardness with the incorporation of particles. So a quick summary of what we've achieved to date in the project as it relates to benefits to the DoD. So the objective number one, the process optimization, results in the DC capability or compatibility, which will result in reduced infrastructure costs when trying to deploy this new technology to conventional plating shops. Pulse plating works fine, it works very well, and it gives you lots of flexibility. But when looking to put this in a new plant, that results in extra infrastructure cost. So it's great that we can get the process to work with conventional direct current plating, which is the current typical type of rectifier you see in plating shops. The lower operating temperature now should reduce processing costs and improve the ease of operation and compatibility with various masking waxes. So that is a good advancement. The plating on aluminum can enhance the strength of aluminum with minimal weight addition. And both the R3010, which is the conventional Cobalt Phos, and the 3311, which is the process modified for aluminum, are suitable for plating a number of substrates, including steels, polymers, and polymer composites, if you want to extend the technology to new applications. Related to Objective 2, the composite generation. It improves in superior performance on the coatings, both in terms of hardness and taper wear, ultimately hopefully resulting in improved field performance and extended life of components. And the extension of the technology to brush plating systems allow it to be used for possible field repair of components, so less costly. So now going forward in the project, we've more or less solidified the operating window and locked down on the chemistries going forward. And now we're moving into a small little validation test program where we're looking at the composition, microstructure, adhesion, microhardness, ductility, wear, corrosion, and hydrogen embrittlement of the lockdown process at a larger scale. So we hope, we're very excited about the results that will be coming through, and we're quite hopeful that it will do as well as we hope. So with that, I'm happy to take any questions that anyone might have.
Thank you, John. I would like to remind our audience to continue submitting questions by using the chat box on the left-hand portion of the screen. We have received a number of questions, and I'm going to pose them to you, starting with, from an industrial application perspective, John, what are the main advantages of Nanovate Cobalt Phosphorous coatings as an EHC replacement?
Yeah, I would say the main area that we've seen the biggest uptake, chrome is a good coating, and it's been used a number of places, and people are, it's very hard to change somebody's use of a material unless they're forced to. But in areas where there's actually a process and cost benefit has been in areas where there's use of hydraulic cylinders in chloride environments. That in that specific use, there's actually a very definite, very significant improvement in the lifetime of the product. So you can easily put it on the hydraulic cylinders, and you get improved performance compared to chrome, specifically when you have that high chloride corrosion present.
Thank you. A question from Boeing. Can you please comment on the salt spray requirements and performance of nanostructured coatings versus hard chrome?
Yep. In the slide that I previously showed, when you get significant, due to the fully dense microstructure and no micro cracks, you do see significant improvement in the time to red rust versus electrolytic hard chrome coatings directly deposited onto steel. The one, probably one issue or thing I should mention with the Cobalt Phos compared to chrome is there is a tarnish that forms with the Cobalt Phos. So although it forms a very thin kind of cobalt oxide, which has kind of a brownish color. So that forms fairly early on in salt spray, but doesn't progress any worse than basically looking like a bit of a stain on the material. But that aside, from time to red rust and performance in salt spray, it does very well and does protect your steel components much better than hard chrome.
Thank you so much. A question from Sikorsky Aircraft, actually question comment. Corrosion for chromium is via electrolyte traveling through cracks to the substrate. What is the mechanism for substrate corrosion through Nanovate since there are no cracks or porosity?
Yeah, I think that's a good question, and I think one of the reasons why it does very well in the long-term corrosion testing. I'm not sure. I know in a number of cases, typically with the Cobalt Phos in salt spray corrosion, we've taken it to about 1,000 hours, and we don't see any red rust. And I think that's been the case with the previous slide that I showed, which listed at 1,200 hours. I believe actually it was pulled from the sample at 1,200 hours, and there wasn't any red rust. So I think there, from what we know, there's in the salt spray environment that there is no pathway, which is why we don't see the red rust for quite a while. In some cases, when we do see it, it's most likely related to kind of processing defects due to improper processing of some test samples, which people that are familiar with plating are probably well aware of.
Great, thank you. From an industrial application perspective, can you comment on the stability of the Nanovate Cobalt Phosphorous plating solution?
Yep, the plating solution is very, very stable even in an industrial environment. I think we've had a few licensees of the technology that have used it industrially, and they've had no issues. Seems to be very resistant to contaminants. And as I said, with our process here, we've never had an occasion where we've had to replace the solution. Sometimes you see some different contaminants come in from the substrates that you're plating. Some of the metals might dissolve a little bit, but they all are managed to come out of solutions and they don't cause problems. So from that perspective, it's a very robust. There's not a lot of additives, not a lot of components that break down. So it's quite usable and quite reliable just from a long-term perspective.
Great. And just one last quick question, and whatever questions we don't get to now, we'll answer in the final Q&A question. But this is in the last session. This is a question from the Navy Research Lab. What was the cause of the decreased taperware resistance with the harder nanocomposite coating?
So the decrease, the taperware index, so that's the mass loss. So you get improved performance as the taperware index goes down. So we believe that through the incorporation of this hard phase particulate, it provides much better abrasive wear performance. The taperware test basically involves rotating a disc against these rubber wheels that have alumina oxide in them. The alumina oxide provides the abrasive component of the wear. And by adding the hard phase particulate to the cobalt phos matrix, that provides quite good resistance to this abrasive wear mechanism that you see from these taperware wheels. So what we found is once you get sufficient volume fraction of the hard phase, of the second phase, kind of hard ceramic particles co-deposited into the cobalt phos matrix, then you see this nice decrease in improved abrasive wear performance.
Great. Thank you so much for a fantastic job in answering these questions. And again, we'll get back to additional questions in the final Q&A session. It is now my pleasure to introduce our second speaker today, who is Dr. Alan Reeves, a chemist at the Naval Air Systems Command in Maryland. Alan's current research focuses on the development and implementation of inorganic coatings and pretreatments for metals and methodologies to assess the shelf life of aircraft sealant materials. Prior to joining NAVAIR, Alan worked for several small technology companies and served as a PI on a number of materials-focused U.S. small business innovation research programs. He has authored 9 peer-reviewed research papers and co-authored 8 patents. His bachelor's degree is in chemistry from the University of Birmingham, and he has a doctorate also in chemistry from the University of Oxford. Alan?
Thank you, Rula. I want to thank John for his excellent presentation. I think it's accurate to say that the work that I will discuss today directly stems from the work that he's talked about. Several years ago, CERDIP funded an effort to look at other potential uses of these nanocrystalline materials. They looked at hybrid wires, they looked at sheet and foil materials, and they also looked at high-load bushings. It was the latter of these that showed the most promise and ultimately led to the program that I'll briefly review today. So the agenda for today, I'll just briefly go over that too. I'll go over the background of the program. Some of this may be duplicative, so I'll apologize in advance. Then on to, again, a quick overview of nanostructured materials. Again, I'll try not to be too duplicative. Then on to our technical approach to the program, followed by some of the progress to date. We are a little bit behind on our original schedule, so perhaps not as much as I'd hoped to discuss today, but we will have some progress to review, and finally some brief conclusions. So the project background, copper beryllium, it's the hardest and strongest of most of the copper alloys, 2% beryllium typically. It's a preferred high-strength bushing material, used in a lot of aerospace applications. It's got high strength, excellent wear properties in terms of low coefficient of friction, high galling resistance. Has other advantageous properties too. It's a non-sparking material. It's non-magnetic. Has good high temperature performance, good corrosion resistance, amongst other properties. The downside is that exposure to beryllium results in a range of diseases: lung cancer, chronic beryllium disease. And the issue is that DoD employees, as other employees, can be exposed to beryllium dust and fumes as a result of the wearing of beryllium-containing alloys during operation, and also during the machining and other fabrication operations. Within the DoD, too, the manufacturing process for copper beryllium bushings results in a large amount of hazardous waste being generated. So we're looking for less toxic alternatives. And the nanostructured cobalt alloy that's the subject of this proposal is, we believe, can meet and exceed these requirements. Okay, next slide is nanostructured alloys. As I mentioned before, of all the nanomaterials evaluated in the Sergent program, the nano cobalt phosphorus alloys exhibited the most favorable properties as bushing materials. They can be fabricated using an electroform process, which is really a metal forming process by which parts are produced through electrode deposition on a model or a form, which is known industrially typically as a mandrel. Process is essentially electroplating, but with thick deposits formed. In the case of bushings, the mandrel is obviously typical cylindrical with a smooth inner surface. The material that results is fully dense, needs no additional heat treatment, has a very smooth inner surface. And if the process goes well, the outer diameter is also relatively smooth, so bushings can be produced with minimal machining. Hence, we consider it a near net shape process. I suppose it might be considered an early additive process, or AM process, but it's not quite a fully additive process. As you can see from the images, it's a process that can be used for large and small diameter bushings. So I'll go into the next slide. This is just a very simple schematic of the process. As I mentioned, sort of near net shape. It's quite cost effective, very little material waste. In contrast, copper beryllium is often machined from a block of material, which for a large bushing creates a lot of waste. Here we deposit the material onto the mandrel, remove the mandrel, and then do a little bit of machining to produce the bushings of a desired dimension. So the advantages of nanostructured alloys, John has mentioned those, governed by the Hall-Petch relation, which is a relation which describes the increase in strength of metals with the decreasing grain size. Effectively, the grain boundaries act as pinning points, so they impede dislocation propagation. And this basically hinders the onset of plasticity and increases the yield strength of the material. This is a relationship that's been known for quite a number of years. I think it was discovered back in the 1940s and 1950s. But with the advent of a lot of nanograin materials, it's been well demonstrated that the optimum grain size is probably around 10 to 20 nanometers. If you go much smaller, there are no further benefits. I'll move on to the next slide. Just a little bit of data. It's very similar to the data that John showed earlier. Just shows the superior yield strength and ultimate tensile strength of some of these nanocrystalline alloys relative to copper beryllium. So I'll move on now to the technical approach for this program. It's a program in which Integran and Navair are the primary performers. There are 5 major tasks for it, first of which is the manufacturing process, definition, and demonstration. This is a task really to look at to optimize the electroform process and identify the process parameters of interest. So optimization is really looking at the set of process conditions and parameters to electroform bushings with wall thicknesses as high as ½ an inch. One of the main targets is to minimize the deposited surface roughness. For the obvious reasons that I mentioned, a smooth electroform surface is desirable. It just minimizes the amount of machining required to grind it smooth and minimizes the amount of material waste. Property and performance testing, again, fairly self-explanatory. Basically, we need to collect enough material data to understand how the material behaves and to generate some initial design allowables such that parts can be placed on board aircraft. Third is to the depot evaluation insertion part of the program. I mean, ultimately the goal is to transfer this technology to Navair depots. We're working currently with Fleet Readiness Center Southeast on this. Jack Benfer, Ruben Prado, who John mentioned in his talk, are the part of the project team and really the primary DoD stakeholders for the program. There is a tank in place at FRC Southeast, but it will need some work to get it operational, and Integran will assist on this. The goal is that FRC artisans are going to be able to produce the necessary blanks, allowing the depots to machine bushings on an as-needed basis. So included in this task will also be an assessment of the machinability and, more importantly, hopefully a demonstration of the technology on board an aircraft, which I'll mention later in the talk. In terms of cost and environmental analysis, we'll look at the costs and environmental impacts of the material relative to current materials in use. That includes copper beryllium. And finally, we will look for material. We're looking towards material qualification. We want to generate a data package which can form the basis, perhaps, for a draft specification, maybe an AMS spec. And ultimately, the goal is to generate sufficient data for inclusion into MMPDS, which is the Metallic Material Properties Development and Standardization Handbook. So in this talk, I'm just going to discuss briefly the results from the first 2 tasks, since these are the tasks which have been active over the past year. Okay, and the first task is pertaining to the tank installation at Integran. Integran's goal was basically to design and construct a dedicated bushing tank, which they did. The specifications are provided here. It's around 400-gallon tank, 1,500 liters. It's double wall insulated, auto level water filled, has out of tank filtration, out of tank circulation, and it's in place at their Mississauga facility outside of Toronto. The goal really is to take lessons learned from this experience and transfer the know-how to Jacksonville. So the next slide. Goal was really to specifically optimize the electroform process for this material, and specifically with the intent of electroforming bushings. Another goal was really to come up with a reusable mandrel design. The initial ones were just stainless steel rods. They were disposable. They were machined out of the electroform. Obviously, this is not a cost-effective process, and from a waste perspective, really not desirable. So that was also one of the tasks. The three key process parameters that were identified were pH, current density, and rotational speed. And so I'll go over these individually. In terms of mandrel design, we looked at 4 different designs. I probably could have used some images here, but we'll just go with my descriptions instead. The first of these was a metal sleeve with a collapsible interior core. The sleeve was prepared at Integran. It was a nickel cobalt sleeve. So you lock the core in place. It holds the sleeve rigid, plate on top of that, and at the end of the plating process, the core collapses and is removed along with the sleeve. Design number 2 was a metal sleeve with a polymer core, a solid polymer core. The core fits loosely at room temp, but as it expands at the deposition temp, it fits snugly then, and then on cooling can be removed along with the sleeve. Third design was basically disposable, was machined out, and then the 4th design was a metallized polymer core, similar to design number 2, but basically in this case the core was directly metallized instead of being a sleeve. So Integran came up with a ranking criteria for each of these designs, and they conducted a large number of trial runs for it. In terms of ranking, of course, red is worst, green best. Overall of these, of the 4 designs, design number 4, which is the metallized polymer core, probably that was overall the best. All had some merits. I think the conclusion was that ultimately the type chosen may be somewhat dependent on the application. Maybe for one-off designs, design 4, which is the lowest cost, may be best. For higher end applications, perhaps design 1 may be better, since it's a little more durable. In terms of process optimization, I'm not going to go into huge detail regarding the 3 process parameters. Integran did a large amount of empirical evaluation looking at each of these parameters, both individually and in conjunction with one another. In terms of pH, what was determined was that it was found that at low deposition thicknesses, the surface roughness, the outer surface roughness, really was somewhat independent of the typical pHs employed in these baths. However, as the thickness deposit increased, a lot of nodule formation was observed. And this was actually found to be reduced just simply by increasing the pH of the solution. The picture in slide 53 shows deposits of similar thickness. Those on the left were produced at a lower pH, and those on the right at higher pH. There are clear differences. Obviously those on the right are quite a bit smoother than those on the left. There are still some nodules there, so there's still some minor improvements needed. But overall, it did show that increasing the pH to a specific level was important for producing thick deposits. Similarly, for rotation speed, slide number 54, at low thickness, the rotation speed didn't have a significant effect. But when we went to higher thicknesses, a low rotation speed also led to a lot of surface roughness. And you can see all the nodules in the image on the left, which is significantly reduced when the rotation speeds were increased. So current density was the final process parameter that was looked at. Electroform processes typically use very high current densities. And initially, for low deposition thicknesses, there really wasn't a whole lot of effect. But as it started to get around 5 to 10 millimeters thick, and you can correct me if I'm wrong here, John, roughness became more of an issue. And it was found that if at this point you just started to reduce the current density just slightly, the issues were largely resolved. And although the coating rate was diminished slightly, the effects really weren't significant. So these were the three process parameters of interest. The process is now considered fairly stable. All of these parameters have been optimized for the electro deposition of nano cobalt phosphorus for the bushing application. In terms of process verification, Vickers micro-hardness has been primarily used to assess the uniformity of the deposit, and through thickness measurements really haven't shown much variation in thickness at all. It's very, very consistent, around 550 Vickers number. The blue line in the plot on the left shows the point at which the current density was changed during the deposition process. And as you can see, it really didn't have much effect on the material hardness. In terms of other process verification techniques, some NDI has been performed on these electroforms, CAT scans primarily. We have found no voids in the material, and the analyses have been done both on the as-fabricated blank materials and on the fully machined bushings. I think the voxel size for the blank material was around 15 microns, maybe a little lower for the fully machined bushing. So certainly any voids that are in there are smaller than that, which in terms of property and performance testing, we have developed a joint test protocol. It's fairly detailed, and I'm not going to go into all the proposed tests here. In terms of mechanical testing, the main tests that are planned are tensile testing, compression testing, and fatigue testing. Obviously all key properties for bushing materials under high load conditions. We also plan to do significant subscale bushing testing here at NavAir, and also some galvanic compatibility testing. That's obviously a key issue, making sure that any bushing materials are compatible with primarily aluminum aircraft alloys. In terms of the bushing testing, we did some initial subscale tests. They were tested according to an SAE spec 81934, which is a test for unflanged bushings. It's normally applied to a Teflon line bushing, the Teflon really acts as the wear surface and the lubricating surface. So it was a very demanding test for this, which was for these materials since they were run unlined. However, although the absence of the liner meant that the wear requirement wasn't met, the bushings actually showed very linear wear. There was no obvious damage to them. There was no distress on the wear surfaces. And the testers also observed a very low sound generation for these materials, given they were tested in the unlined form. So although it's not an ideal test, and we will conduct future tests on these materials, the results were overall encouraging, and I think they certainly merit future work. In terms of galvanic compatibility testing, we've done some polarization studies of the nano cobalt phosphorus, the copper beryllium, and the aluminum 7075 alloy, common aircraft alloy, indicating some slight improvement in compatibility between the two. If you look at the polarization curves there, which show, I should mention, of course, that in any of these, when we're putting these dissimilar metals together, the aluminum will always, or will generally act as the anode, and the bushing material typically as the cathode. So we have the cathodic leg of the polarization curve for both nano cobalt phosphorus shown and the copper beryllium, and the anodic leg here for the aluminum alloy. What we see is where they cross is the corrosion potential and corrosion current for these couplings. And we see a slightly lower corrosion current with the nano cobalt phosphorus and 7075 compared to copper beryllium. Similar improvements were seen with stainless steel alloys. We have been conducting some galvanic compatibility testing as well. This work isn't complete yet, so I don't have a complete data set to show today, so I will address that at a future date. In terms of depot evaluation, the goal of course, is to transfer the technology to the fleet readiness centers. As I mentioned initially, at Fleet Readiness Center Southeast in Jacksonville, where we plan to stand up the electroforming tank there, perform machining evaluations. And we have identified bushings on the arresting tailhook of the naval T-45 trainer aircraft as a component for demonstration validation. Obviously, the success of this program will depend on a successful demonstration at the depot level. So that will be a key measure of the success of this program. We're also looking at potential applications for ground vehicle applications. There's on the left there a pair of bushings that were prepared for a ground application. So there are quite a number of potential applications for these materials. In terms of the DoD, what are the benefits? Well, the primary benefit, of course, is a significant reduction in the use of beryllium-containing materials, which present less hazards for DoD personnel. In addition to the reduction, there's also potentially significant performance advantages for of the nano cobalt alloy over copper beryllium, and which may lead to enhanced product lifetime, reduced operating costs. From a depot level, the ability to prepare bushings on demand with a near-net shape fabrication capability is quite desirable. Hopefully this will reduce the amount of the turnaround time between repairs and present some certainly readiness advantages. In terms of overall conclusion, where we are right now, an optimized electroforming process for fabrication of bushings has been demonstrated at the lab scale. Materials are void-free and of uniform hardness. The initial bushing tests have indicated some promising properties. They have potentially slightly more favorable galvanic properties, and we've also developed a test protocol for complete evaluation. That's pretty much all I have for today. I'd be happy to field any questions that anybody has. Thank you very much for your attention.
Thank you so much, Alan. We've also received a number of questions for you, starting with the following.
Okay.
Can you please elaborate on the maximum thickness of electroform that can be produced using the process you described?
We have been targeting around a 1/2 inch thickness in terms of the outer wall. Potentially it could go a little thicker than that. It just depends on how long you want it to take. For a reasonable electrodeposition time, we're certainly targeting up to about a 1/2 inch thick, so 12 to 13 millimeters.
Thank you, Alan. A question from Lockheed Martin. Can the magnetic shielding performance be extended into the microwave region?
Honestly, I do not know the answer to that. I can defer to John. John, do you have any idea on that?
I think with magnetic shielding, it is a ferromagnetic material. It would have some soft magnetic properties, so it should have some magnetic shielding in the low frequency range. I believe at higher frequency, you get basically conductive materials do shielding. With the higher conductivity, the better performance. So I think it would provide shielding, but how well it does compared with other materials would probably you can compare the electrical conductivity of the coating, which we have values for.
Thank you both. And John, since you're back with us, can you both weigh in on any safety concerns with the use of nanomaterials? Starting with you, Alan.
In terms of these materials, there really is no issue with their use. As John, I think, mentioned in his talk earlier, no powder materials are produced in this, so the size of the grain is really unimportant in terms of the safety aspect of it. They are essentially just metallic materials and have the same hazards associated with any metallic material.
Do you have something to add?
Avoiding. Yeah, no, I think Alan, I concur with Alan with what he said. I think, a question, I mentioned there's no particles, so they deposit as solid materials. We have been asked the question as to, during machining or grinding, do you expect nanoparticles to be released? And we believe they would machine, as you machine or grind away, you wouldn't grind away individual nano grains. You would probably take, through machining, when we've machined these bushings, they machine just very similar to other metallic materials where you get strips come off, so they're ductile. So we expect that even through grinding or machining, what is released will be metal, and there'll be, some might be particles, but we think it would be comparable to conventional processing of metals where the particle size isn't really related to the grain size, but consists of multiple grains. So we don't think there should be any issues pertaining to the nanocrystalline grain size.
Great, thank you both. And then for you, Alan, are there any limits on the size of the bushings that can be produced?
The bushings are really determined by the size of mandrel, so that determines the diameter. One limit that might be would be for a very high aspect ratio flange bushing, where it had a very, very large flange on, because obviously that would require a very thick deposit. But for most typical bushings, certainly unflanged bushings, there shouldn't be any limits or significant limits. And with a flange, as long as the combined the flange thickness isn't too great, it shouldn't be an issue.
Okay, so the performance does not seem to be an issue, but what about the cost of fabricating these nanostructured bushings relative to the conventional bushings? Can you address that, Alan?
We've done some sort of preliminary cost analyses, and whereas the effective material cost of the nano cobalt phosphorus alloy is higher than, say, copper beryllium, in terms of machining the final bushing, because so very little material is wasted relative to copper beryllium, they're quite competitive in terms of cost. And in fact, as you get to producing larger bushings, particularly with copper beryllium, where you're machining out more and more material, they actually become, in theory, lower cost.
Oh, that's really interesting. Thank you. John, we got a question earlier from the Army Office of the Assistant Chief of Staff for Installation Management, and it relates to whether the Army Public Health Command has evaluated Nanovate Cobalt Phosphorous. Are you aware of any efforts from that office?
I am not. No, I'm not sure. I've heard of. I don't know.
Thank you. And then a question for both of you, and perhaps you can start responding to that, John. Can you comment on the current and proposed regulations regarding cobalt air emissions?
With the current, I'm not aware of any changes to any or reductions in the air emissions, but currently a number of tests have been done kind of on the emissions coming off the tank, both here at Integran as well as at Fleet Readiness Center Southeast. And all the emissions off the tank are well below the current regulations, which I believe are quite stringent and actually lower than that of chromium. So we don't believe there will be any issues with the current regulations. I'm not aware of any changes to those.
Alan, would you like to add anything to that?
I would concur with John. I mean, I believe there were a number of salts, cobalt salts, proposed for inclusion in the authorization list for REACH regulations, and I understand that, or I know that these are not residual in the coatings produced, and that the bath can be prepared without them. In terms of machining the materials, I mean, they would have the same issues as any other cobalt superalloy that are commonly used out there today.
Thank you. And Alan, are you aware of other nanomaterials that could be suitable for repair and replacement of high-wear parts? I'm not too familiar with nanomaterials that are used for high-wear parts now. I know there are many alternatives out there. Okay. Thank you. John?
Well, I know that from our from our own list of metal coatings that we can conduct, we as part of the early SurgeRip effort on the copper beryllium replacement, we did look at other nanomaterials. So we looked at a nickel cobalt alloy as well as the cobalt, and although those are so we actually looked at cobalt phos, pure cobalt, as well as a nickel cobalt. So the interesting test was between the cobalt and the nickel cobalt nano alloys that we looked at, they were both the same mechanical strength. If you looked at the tensile stress strain curves, they both looked very similar. But in the subscale bushing tests that we did, we found that the nickel cobalt alloy failed the test while the pure cobalt passed. And we believe it's due to the pure cobalt and the cobalt phos have very, very interesting friction and wear performance, and we think that low friction, low galling performance of the cobalt made it perform very well. So in that aspect, it does seem that cobalt or the high cobalt alloys are very unique in terms of performing that high wear, high load kind of performance that high load bushings require.
Great, thank you. And then one last question before we wrap up. Certainly the materials that you described have a lot of uses for the high wear parts issue, but do you believe that these materials are applicable beyond the aerospace industry, or do they have the potential for more widespread commercial use? John?
Yeah, we believe there's quite a variety, quite a variety of different applications where the materials can be produced, both in kind of electroforming applications like we're looking at with the bushings, as well as with coatings, protective coatings, as we've been doing with the hard chrome replacement, nickel replacement. But there's also quite an interesting use of the materials as kind of hybrid structures, similar to how we looked at it with putting the coating on aluminum to strengthen it. There's a lot of different interesting things you can do by combining the high-strength structural coating with various substrates, such as injection molded polymers or carbon fiber composites, as well as additive manufactured polymers. So yeah, there's quite a variety of different applications where these materials can be used.
Thank you, John. Alan, would you like to add anything to this?
I think in terms of the bushing application, I think any application that where high loads are involved and performance is more important than cost, I think there's potential application for these materials. I think we did mention that there's some ground vehicle opportunities that have been looked at, and I think they will be followed up. I think there's, in terms of heavy ground vehicles, there are probably some uses there.
Great. Well, I'd like to thank you both on behalf of SurgeRip and ESTCP for a very interesting discussion on advanced nanocrystalline alloys as alternatives for repair and replacement of high wear parts. And I'd like to remind our audience that the next webinar is on Thursday, April 18. It is in the munitions response area, and it's titled Sediment Volume Search Sonar. This webinar will feature one speaker, Dr. Daniel Brown, who is a research and development engineer at the Applied Research Laboratory at the Pennsylvania State University. As Robin mentioned, registration is open for this and other webinars through the end of the calendar year, so please make sure to visit the SurgeRip and ESTCP webinar webpage for registration information. And before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on the webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you could please take a moment to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you so much for your attention.